Friends, imagine something like this. In just 1 second, yes, you heard that right. In just 1 second, something that can circle the entire Earth 7 times. Yes, what I'm talking about is light. For centuries, it has fascinated scientists. The magnificent thing that we know nothing in the universe moves faster than, and the very thing that makes it possible for us to watch this video right now. And of course, perhaps thanks to Albert Einstein's special theory of relativity, it has become one of the most popular topics in science. But first, let me play a little game with you. I'm going to make two crazy claims about the speed of light. Let's see if you can guess which one is correct. Claim 1. If you turn on the headlights of a spaceship traveling close to the speed of light, someone watching from outside would not measure the light coming from the headlights as speed of light plus speed of the ship, but simply as the speed of light. Claim 2. When we look at our neighboring galaxy, Andromeda Galaxy, we see it as it was 2.5 million years ago, because even light, the fastest thing in the universe, takes that long to reach us from Andromeda. But if we got into a spaceship and went there, even if we were slower than light, we could arrive having aged only a little. Were you able to guess? Was it too hard? Too easy? Before you decide, think a little more, because this situation sometimes even surprises physicists. But to answer big questions, we first need to build our foundations very well, so we must understand the nature of light, something that has puzzled even the greatest minds for centuries. What exactly is light? Without a doubt, we owe our ability to watch this video to it, right? But what our eyes can see is actually a very small part of the light spectrum, just a narrow region we call the visible range. The fundamental particles of light, photons, have different energies and appear in different regions. For example, X-rays, the microwaves in microwave ovens, the infrared light in remote controls, or the radio waves used in communication. In fact, they are all the same thing, photons. They just have different energies. That's why their effects and uses are different. This is where the word radiation comes from, meaning to radiate, to emit light. When we say radiation, we usually mean high energy, ionizing, harmful radiation, like X-rays. But the only difference between that and the light that allows us to see is its energy. So one of light's most fundamental properties is its energy. But there is an even more fundamental property that has astonished scientists for centuries. It's speed. Now let's go back a few centuries. You are a scientist, sitting at your desk in the light of a candle on a cold, rainy night. Raindrops tap against the wooden window frame. As your breath flickers the flame, you watch the shadow of your feather quill dancing. Then it occurs to you, how long does it take for this shadow to form? How long does it take for light to travel from the candle to the table? I know it happens in the blink of an eye because I've never seen it move slowly. Then, if I want to measure it, I need to increase the distance. What if I synchronize my clocks with a friend and climb two neighboring hills at the same time? If I suddenly turn my lantern off and on, how long does it take for that light to reach my friend? Like many other things in science, someone had already thought of this idea. And, of course, it was tested many times. We know the person very well for many important discoveries. Galileo Galilei. However, Galileo's attempt did not go very well. No matter how hard he tried, the light between the two hills behaved just like the candle lighting up the table. It was simply too fast. His conclusion was naturally, at least it is too fast to be measured this way. At this point, the obvious question arises, why should light even have a speed? What if it has no speed at all? What if it reaches everywhere instantly? Just because other things we see have speed, does it necessarily mean light must have one too? Maybe it reaches its destination the moment it is created. Why not? After all, what we experience, what we see with our eyes, is seeing light at the moment it is produced. It appears to hit our eyes instantly. We have no evidence to the contrary. Why would anyone stubbornly try to measure it, especially when even Galileo couldn't get a solid result? This is exactly why we developed the scientific method. Our intuitions, perceptions, and experiences, our own minds, are very prone to error. That's where scientific skepticism comes in. And of course, it doesn't end with Galileo's unfortunate attempt. Despite Galileo's great reputation, someone tried to improve his method. One of the strongest aspects of science is that it is constantly tested and reviewed by many independent people. And such a method did exist. In 1676, just 34 years after Galileo's death, the Danish astronomer Ole Romer came up with a brilliant idea. He realized there was a way to measure the speed of light by tracking the moons of Jupiter. The first few visible moons of Jupiter are called the Galilean moons because Galileo first observed them. These are Io, Callisto, Europa, and Ganymede, moving very quickly around the planet. Sometimes during their motion, they disappear behind Jupiter's massive body. An eclipse occurs. Romer measured the duration of these eclipses when Earth was closer to and farther from Jupiter. Since we orbit the Sun, as the distance between Earth and Jupiter increases, light has to travel a longer distance. He noticed the eclipses were delayed, and as the planets moved closer, the delay shortened. So light traveling between the two planets takes measurable time. This was an incredible discovery. It meant light does not reach its destination instantly. Romer calculated the speed as 220,000 kilometers per second. Today, we know it's approximately 300,000 kilometers per second. Considering this was calculated nearly 350 years ago, it was astonishingly accurate. Now let's return to speed. In 1905, when Albert Einstein published his famous paper on the electrodynamics of moving bodies, he introduced a completely different perspective. He proposed two fundamental postulates. One of them almost rebelled against the physics of the time. Observers moving at constant velocity, regardless of their own speed, must always measure the speed of light as constant. Let's understand this with an example. If you're in a car moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone outside measures it as 150 kilometers per hour. Easy, right? But if instead of a ball you turn on the headlights, intuitively you might think car speed plus light speed. But no, light speed does not add that way. It is always measured the same. Einstein showed that velocities don't simply add, they follow a different formula. As speeds approach the speed of light, the difference becomes significant. And no matter what, the result never exceeds the speed of light. It only approaches it. And this is not just theory. It has been confirmed countless times through independent experiments. Now, back to the second claim. You might think it must be wrong, especially since nothing can exceed light speed. But surprisingly, it's also true. One of the unintuitive consequences of relativity is time dilation. If your twin travels near the speed of light and returns after 10 years on Earth, they may have aged only months. This sounds like science fiction, but it's a verified reality of our universe. We haven't sent twins at near light speed, but we observe these effects elsewhere, especially in GPS satellites, which must account for relativity to avoid massive positioning errors. Experiments at CERN accelerating particles near light speed also match Einstein's predictions perfectly. So today, whether we realize it or not, we use technologies built upon discoveries that started with Galileo, continued with Romer, and were formulated by Einstein. So traveling to the Andromeda Galaxy, 2.5 million light-years away, might be possible in a human lifetime if you travel near light speed, though millions of years would pass on Earth. The problem? How do we reach such speeds? We are biological beings, and our bodies can't handle unlimited acceleration. But scientists calculated that even with just 1 g acceleration, the same we feel on Earth, a round trip to Andromeda could take only 50 years for the traveler. Meanwhile, millions of years would pass on Earth. So yes, both claims were true. When I said it was a little science game, I didn't mean just those questions. The real game is science itself. Without an answer, key to the universe, distinguishing right from wrong is not easy. Science is not about blindly believing Einstein. It's about independent minds testing, questioning, correcting, and reaching consensus. But science is also not denial. It requires the ability to accept correct results. Otherwise, we cannot build upon them. Otherwise, our compass will always point in different directions. And we will lose our way. If you enjoyed the video, don't forget to like it. See you next time. And as always, stay well. Always.